this chapter, we're going to explore the calculus of exponential and logarithmic functions. In this lesson, we're going to do a quick review of the properties of exponential functions.
All right, hi everybody. So now we're going to take a look at the calculus of exponential functions. And actually this is one of my favorite chapters to work with. You can't overstate the importance of these exponential functions in math in general, in calculus specifically. And this is going to be great. Some of the rules here are they're so nice in this particular chapter here. But anyway, before we get to that, let's kind of back this up a little bit. We're going to talk about exponential functions just a very, very little bit. I'm going to assume a lot of the groundwork has already been laid. What we're going to do here is just take a look at what some of the limits are. Okay, so remember that an exponential function, is of the form, okay, here we go. So y equals b to the x, okay, where x is an element of the reals, and b is also an element of the reals, okay, but we're going to say that b is greater than 0, and more specifically, b is not equal to 1, okay? Now, it's not that b couldn't be less than 0. Now, b equal to 0 is just completely useless. That probably does count as an exponential function, but I mean, it's not going to give us any useful information here. But b less than 0, that does work, but it's going to create imaginary numbers or complex numbers here, and we're not interested in that for right now. And we're not going to let b equal to 1, because just think about what that would be. If b is 1, 1 to the x is just going to be 1. It's going to be not very interesting, and some of the conversions there wouldn't make any sense if the base is equal to 1. So let's take a quick look at what that looks like here. So let's consider, and we're going to probably graph a couple of these things, but consider y is equal to, and let's just make it really straightforward, 2 to the x. What does that look like? Okay, well, here's our coordinate plane. Well, 2 to the x would look something like this. Okay, your exponential function would look something like this, specifically going through the y-axis there at 1. Okay, so, and this is basically what's going to happen here. Anytime you've got a function like this, your domain is going to be x as an element of the reals. Now I could probably write that out a little bit cleaner using set notation or interval notation here, but anyway, my range is going to be the set of values where y is greater than 0, not equal to 0. At no point will it ever equal to 0, although it'll get closer and closer and closer, and so as a result, we know that its behavior is asymptotic to the x-axis there. Okay, it's going to approach 0 as we go to the left there, and we're going to talk about that in just a second here. X-intercept, well, shouldn't have one unless it's been translated up or down. Y-intercept is going to be equal to 1. Okay, and let's just take a quick look here. If I take the limit as x goes to positive infinity of 2 to the x, the answer is going to be infinity. Okay, as I go to the right, this graph is just going to shoot up, and it's going to go up really, really fast. Okay, I mean that's what we mean by exponential growth. We imply that it grows really, really quickly. Well, in fact, it does grow really, really, really quickly. If you take the limit as x approaches negative infinity of 2 to the x, I want you to think about what that's saying there. Okay, and actually I want to make a connection between this relationship here and another one here, because watch what happens if I let the exponent become a negative. Notice that's going to cause a reciprocal here. Now I can see on my graph here that as I go to the left here, that's going to approach 0, but I want to see another connection here. If I just take the negative off of this, and bearing in mind that I'm going to approach negative infinity, I'm going to let x approach negative infinity, I'm going to take that negative off and I'm going to permanently attach it to that. So I want you to know here that this would actually be equivalent to the limit as x approaches, let's say, positive infinity of 2 to the negative x. If I just pull that negative off and kind of permanently attach it to the exponent there. Now, think about what this is. Okay, this is actually going to be the limit as x approaches infinity, positive infinity. Well, what does a negative do in the exponent? It causes a reciprocal. So 1 over 2 to the x. And because of the nature of 1, I can really make this the limit, whoops, I don't want to get too far here, as x approaches infinity of 1 over 2 to the x. Now bear in mind that my x here, when I write it like this, is distributed to both the numerator and denominator here, but 1 to the x is just going to be 1, so that's not going to make any difference here. So this is 1/2 to the x here. So as x goes to infinity of 1/2 to the x, my answer here is going to be equal to 0. And that's because I made the connection between this one and this one right here. Now, if I graph that, and hopefully you're familiar with this, if you graphed 1/2 to the x, it would look something like this. Okay, so this right here would be y equals 2 to the x. This one over here would be y is equal to 1/2 to the x. Okay, and I'm basically achieving this one by simply putting a negative in the exponent here, and a negative in front of the x, thinking back, is going to cause a reflection over the y-axis, and that's why it looks like that. So there you go. Okay? So really, we can start making up some rules here now, based on what we just saw here. So if the absolute value of r is less than 1, and this because although we don't typically talk about the base being negative here very often, in this particular case here, even if it was negative here, it's still going to give us the same limit here. So if r is less than 1, the limit as n goes to infinity of r to the n is going to equal 0. If you're dealing with some sort of fractional value here, and you let its exponent go off to infinity, whether the base is positive or negative doesn't really matter here. If you let the exponent go off to infinity, you're going to get it becoming a 0. And now just think about what that's doing, what that means here. Let's take, for example, a half. If you're not sure kind of what's being said here, the absolute value of a half is less than 1. Okay, we are talking about, when we say this right here, we are talking about numbers along the number line here between -1 and 1. Okay, we are talking about numbers in this interval right here in between. Okay, big open circle, however you want to draw it, it's in between. Whoa, you can't see that at all. Wow, I'm sorry. I got -1 and 1 here, and I've got the endpoints of that interval there. We're talking about numbers between -1 and 1. Pick any number in there, like a half, and let the exponent get larger. A half squared is a quarter. A half cubed is an eighth. A half to the fourth is 16th. It's getting smaller and smaller and smaller, and so as n goes to infinity, it'll approach 0. Okay. Likewise, okay, if r is greater than 1, and this time we're not gonna talk about positive or negative here, because negative is gonna get a little bit more confusing here. If we take the limit as n goes to infinity of r to the n, in this case that's going to go to infinity. And same thing here, again, if r is greater than 1, if I take the limit as n goes to infinity of 1 over r to the n, and now let's think about what I'm saying here. If this previous line here is true, then this is going to cause the denominator here to go off to an infinity, and 1 divided by an infinity there, that's going to approach 0. Okay, so those are the relationships that we want to deal with. Now, let's take a look at a couple of questions, and then we'll start looking at a little bit more of the behavior of exponential functions. Okay, so let's just run through just a small handful of examples here. Again, just to emphasize the behavior of these exponential functions. So I've got 4 to the x. Okay. Notice there's nothing really particularly interesting about that base there. It's a positive number greater than 1. I'm letting x go off to infinity, so when that happens here, that is simply going to become an infinity, okay? Because I can tell right now, I can see in my head that this graph is going to look something like that. Okay? If I let x go to infinity of 3 to the negative x, Well, now let's think about what that negative is doing here. Let's just rewrite this limit. This is x going to positive infinity. But let's deal with that negative exponent. That's going to be the same as 1 over 3 to the x. Okay, well now I've got a better image as to what's going on here. X is going to infinity. 3 to the x is simply going to be an exponential function like the one above it. So that's going to go to infinity, but that means I've got the denominator getting exceptionally large, so the fraction here is actually going to approach 0. In this case right here, I've got 1/2 to the x. Okay, 1/2 to the x. Remember, we just looked at that. That's going to look like this. And if I let x approach negative infinity, I'm going this way this time. Well, I can see right now that this is going to go off to infinity. Okay, and I could have approached this a different way here. Again, by pulling the negative off of that and fixing it to the x here, which would cause this whole thing to reciprocate. Okay, which caused the base to reciprocate and make this 2 to the x. Okay, 2 to the positive. 1/2 to the negative x behaves the same way as 2 to the positive x, and that would go off to an infinity as well. Here, that is actually the approach that I'm going to take here, and I'm going to do that here because notice that my base here, as a fraction, most people are going to kind of respond to that going, why did it have to be a fraction? But notice that my numerator is larger than my denominator. So what I would personally do when I see something like this is, because I can see that I'm going to negative infinity here, I would take that negative off and throw it up here and make this equal to the limit as x approaches infinity of 3/2 to the negative x. And then I would know that that negative is going to cause a reciprocal. So this will become 2/3 to the x. I know that that 2/3 is less than 1. And so when I let the exponent go off to an infinity, this is going to approach 0. That's one way to approach it here. You could also see this, if you're comfortable enough with this, and recognize that this is greater than 1. Okay? So because that's greater than 1, its graph will look something like this. And if I am approaching negative infinity, that means I'm going this way on my graph. And I can see visually that that's going to approach 0. So there are a few things I can do to investigate the behavior of this, each of these functions here. Okay. Now, one of the things that we are going to include in this that you're going to have to consider is what happens when we perform transformations on these graphs. And we'll take a look at that idea using a couple of other examples. All right. So now let's take a look at this exponential function, but let's throw in just a handful of transformations here. Now we're not going to do a ton with this, just a few. Again, just to get you back thinking about exponential functions. So I'm hoping that a lot of this makes sense here. So let's take this first one here. Let's define our function to be 2 to the x plus 1. Let's think about what that is. Okay, here's my function. Okay, my original base function, if you will, and then I've added a plus 1 to it. So this is a vertical translation of 1 unit upward. Okay? So graphically, what that's going to look like is, instead of being a function, and I'm going to assume that this is my number 1 here, instead of this being a function that slides along the x-axis now and works its way up, what this is going to be here is it's going to be a function that slides along the line y equals, y equals 1, and then it's going to shoot up like that. Okay? So what's its behavior going to be like? Well, if you take the limit as x approaches positive infinity of f of x in this case, think about what that's going to do. 2 to the x is going to go off to an infinity, and then you're going to add 1 to it. Now, please don't be the person who goes, oh, that's infinity plus 1. Yeah, no, it's just infinity. Adding 1 to infinity doesn't change it. Yeah, please don't get thrown off by that. Infinity plus 1 is infinity. Now, let's take a look. If you take the limit as x approaches negative infinity of f of x, notice that that's going to affect this term right here. If you take just 2 of x, again, which would ride along the x-axis and work up like this. If you go to the left on that, as far as you can go to the left, that function's going to approach 0. But in this case, that would go to 0, but I've got this plus 1 here, so this would simply be plus 1. Okay? So as I go to the negative infinity, my answer here is going to be positive 1. We just need you to know that. Okay? Let's take a look at another one here. Let's say I've got f of x is equal to the x plus 1. Well, what's going on here? Well, this is a horizontal translation. Okay? Horizontal translation. 1 unit. Now it's plus 1 there, so it means I'm going to be going to the left. So let's take a quick look at what that would look like. Okay, so I'm actually going to write this out here. And in this case, just to help myself out here, I'm going to draw, here's what the original would look like. Y equals, it was going to slide along here and going to come up. This would be y equals 2 to the x. 2 to the x plus 1 is going to be shifted 1 unit to the left. So it's actually, instead of going through the y-axis at 1, it's actually going to go through the line x equals negative 1 at 1. So it's actually going to ride along here, and then it's going to come up like that. And so here is going to be my y equals 2 to the x plus 1. All right. Well, what is that going to do? What is the limit as x approaches infinity of f of x in this case? Well, here I got a very similar sort of thing going that happened up here. Remember, if you take infinity plus 1, you're just going to get infinity. Well, here's the same thing. If you let infinity plus 1 up here, that's just in the exponent. That's still going to be infinity. That's still going to be an infinite value. It's just going to get infinitely large as you go to the right. What will the limit be as x goes to negative infinity? Well, we can see that a horizontal translation actually won't affect the y-coordinate here as I go to negative infinity. And so as a result here, this is still going to just approach 0. Now, let's do the last one there. We're going to slap a negative. Whoops. Sorry, I went too many pages over there. No, that's okay. We're going to slap a negative in front of that. Y is equal to negative 2 to the x. What is that going to look like? Well, it's going to take my graph here and it's going to reflect it over the x-axis. And so now this is going to look like this. Okay, down here at negative 1. And so I just have to remember that that's what's going on. So if I take the limit as x approaches positive infinity of my function here, notice what's going on here is I'm basically, it's still just obeying what's going on right here, just 2 to the x. I'm ignoring that transformation right there until I get my answer, which would be infinity. Slap the negative on. Oh, this is going to negative infinity. So it's dropping down. But as I let x go to negative infinity of f of x, notice that it doesn't really matter whether it's above the x-axis or below the x-axis. As we go to the left here, it's approaching the x-axis. It's just in this case, it's doing it from the negative side. So here again, the limit is still going to be 0 in spite of the fact that I've flipped this thing over the x-axis here. Now, I am not going to reflect this by putting a negative up in the exponent because we've already looked at that. We've already seen what happens when you reflect it over the y-axis and how that changes those limits there. Okay, so let's take a look at kind of a general summary statement here, and then we'll do just a few more examples. Okay, so I know that we've already said this, but now we're just going to write this out. So in general, if b is greater than 1, okay, then the limit as x approaches infinity of b to the x is going to be infinity. And the limit as x approaches negative infinity on b to the x is going to equal 0. And you don't really need to memorize that. You can you can apply these limits simply by remembering what that looks like. Okay? On the other hand, if, let's say, b is between 0 and 1, and again, this does work if it's negative as well, but anyway, between 0 and 1 here, then the limit as x approaches infinity, of b to the x is actually going to end up being 0, because now what's happened is this is reflected, and so this one up here is a graph that goes up like this, but this one down here, this is going to end up being a graph that goes down. So it's going to approach 0, and the limit as x approaches negative infinity of b to the x is actually going to equal infinity. Okay? And so if you just remember this material here, what you're going to see is as we put these functions together to do more and more complicated functions, it's really just these zeros and infinities that are going to get transformed, if you will. So remember, multiplying infinity by a positive number doesn't change anything. Adding numbers to infinity doesn't change anything. By the way, subtracting numbers from infinity doesn't change anything either. Multiplying it by a negative will, and we saw that with our previous example up here. We're putting a negative in front. Well, that'll change it a bit. It changes the directions it goes, but it's still going off to an infinity. So if you bear in mind these properties and then just think about how the transformations would affect these, you can basically handle any of the limits that we're going to be working with. And then in our next lesson, when we take a look at building derivatives, okay, we have to go back to first principles. We're going to see some really interesting results there. But anyway, let's take a look at just a handful more examples. Okay, so let's just finish off with this small little handful of examples here. First, we're going to take the limit as x approaches infinity of 8 to the negative x squared here. Okay, so notice that I've got this negative up here in the exponent. So that really does imply, well, you could see this one of two ways here. You could either see this as converting this to 1 over 8 to the x squared, okay, 1 over 8 to the x squared, or you could see this as 8 to the x squared being reflected over the y-axis. In either case here, as x goes to infinity, x squared is going to go to infinity. This is going to become negative infinity, okay, which means a reciprocal here. And so really what happens here is I've got this fraction where the denominator is going to get really, really large. This is going to go to 0. Now, if we do the exact same function here and we let x go to negative infinity this time, how does that change my limit? Well, actually, in this case, it doesn't, okay? Because remember, when I take these limits here, I'm looking at what's going on with the x. And when I look at my x here, it's negative x squared. But what comes first? Do I multiply by the negative first here, or do I square it? Well, according to the order of operations, I would do the squaring first. So that negative goes into the x here, it gets squared first, it becomes positive, and then I slap the negative in front. So both of these are actually going to behave in exactly the same manner here. So whether I go to the left or the right, okay, this function here is actually going to approach 0 as x goes off to infinity, which is kind of interesting. And actually, when you take a look at this graph here, think about that. If I plug 0 into this, okay, 8 to the 0 is just going to be 1. So this graph is actually going to look something like that. Just a little bump right on the x-axis here. The y-axis. Now, let's take a quick look at this here. Take the limit as x goes to infinity of 1/2 to the x minus 2. Well, here, I've got a fraction, and I've got my exponent going to infinity. So I already know that when I have a half multiplied by a half, multiplied by a half, and with infinite number of them, that they're just going to get, that product's going to get smaller and smaller and smaller. So this is going to go to 0 minus 2 will just be negative 2. Over here, though, if I let x go to negative infinity, remember that what I can do here is I can pop that negative off there and throw that up top here. So we'll make this the limit as x goes to positive infinity of 1/2 to the negative x minus 2. That negative up there in the exponent is going to cause a reciprocal, so this is going to be the limit as x goes to infinity of 2 to the x minus 2. This becomes infinity, and so infinity minus 2, don't go all weird on me, that's just infinity. Okay? Taking 2 away doesn't change how big that is. So anyway, I know that what we've done in this particular lesson is, in many ways, it's been repetitive. Maybe you might even argue that it's been a bit redundant. But I'm hoping that you're quite comfortable with these properties of the exponential functions, because I'm really excited to show you what comes next.